This is lesson 13, in which we'll take a look at how these gates we've been talking about can actually be implemented. We'll look at three different ways. The first, we'll look at how we can use relays, mechanical relays. The first computers actually use mechanical relays. Then we'll see how integrated circuits can be used, transistors. And finally, we'll look at TTL circuits, so-called transistor-transistor logic, which is sort of an older method. Here's the symbol for a relay. Relay is a mechanical relay. You run current through this coil, produces a magnetic field, and will cause this switch to close. So this is a normally open relay, and we'll call C equals 1 when you run current through and actually close it. Now relays come in two forms, normally open and normally closed. Here's a normally closed one. Here, if C equals 0, it's actually closed, so current would run from A to B. And when you make C equals 1, that is run current through the coil, it opens it. So how can you use these two types of relays to form gates? Well, look at this NOT gate. Here's the truth table for a NOT gate. How can we implement it? Suppose we take a normally closed relay and put it here, normally open one here. Then when X is 0, no current's flowing here, so this output Y is connected to 5 volts, so it's a 1. This one's open. However, if we change X to 1, that opens this relay and closes this one, so now the output Y is connected to ground, or 0. So with these two relays, we've just made a NOT gate. How about an AND gate? Well, suppose we take 4 relays, put 2 normally open ones in series from the output to 5 volts, put 2 normally closed ones in parallel to ground, and let's see what happens. If the 2 inputs is 0, we want the output to be 0. Well, these 2 are closed, so they both go to ground. We have 0, these 2 are open. If we make Y1 and X 0, we want the output to be 0. Well, this Y1 will close this one, but this one's still open, so there's no connection from Z to 5 volts. This 1 will open this one, but this one's still closed, so there's still a connection here to ground, so the output's still 0. If X is 1 and Y is 0, we want the output to be 0. Now this one's closed, and this one is open, and this one up here is closed, and this one's open, so again we have this connection to ground. So it's only when they're both 1, both inputs are 1, both of these series relays are closed, so now Z gets connected to 5 volts, both of these are open, and so we get the 1 output. So here's how you can make an AND gate with these 4 relays. How about an OR gate? Well, as you might expect, here we put the 2 normally open ones in parallel and put the normally closed ones in series. So again, if they're both 0, both of these are closed, we go to ground, the output's 0. If we make Y1, that closes this one, so now we have a connection up to 5 volts. It opens this one, which breaks the connection to ground, so the output would be 1. If X is 1, it closes this one, so now we have another connection to 5 volts. This one's open, no connection to ground, the output's 1. And if they're both 1, then both of these are closed. So we go to 5 volts, both of these are open, so we've implemented an OR gate. Now, how can we use transistors to do the work of the relays? This symbol shows what's called an NMOS transistor, and it behaves sort of like a normally open relay. That is, if C equals 1, that is this voltage here becomes higher than this voltage B, say, then this A gets connected to B, so you can think of it as a kind of switch. A PMOS transistor, this denoted by this little bubble here, this behaves like a normally closed. That is, when C is equal to 0, if this voltage is 0, then it's closed. If this is 1, it opens up. So we have two NMOS and PMOS transistors, which behave sort of like a normally open and normally closed relay. So you think we might be able to just use these like we use the relays. Well, let's try it for the NOT gate and see if it works. It in fact will work. If we put a 0 here, this is normally closed, this is normally open, and so now the 1 is connected up to here, and the output Y behaves like a 1 connected to 5 volts. On the other hand, if this is 1, it closes the NMOS transistor, opens the PMOS one, and so Y is connected to ground. So that works. Now, the reason it works is because the PMOS transistor likes to be connected to 5 volts, and this NMOS one likes to be connected to ground. That is, if you tried to put the NMOS one up here, then you wouldn't get a very good short circuit, and the same as you put the PMOS one down here. So in this case it worked. But you may recall that when we made an AND gate, we used the normally open relays connected to the 5 volts. So it's not going to work to try to make an AND gate like we made it for the relays. In fact, let's see what happens if we take 2 PMOS transistors, put them in parallel, and 2 NMOS ones in series. This is a possibility because the NMOS's one, remember I told you, have to go to ground. The PMOS ones have to go up here to, say, 5 volts. And as we'll see, this is going to produce a NAND gate rather than an AND or OR gate. We can check it out. Suppose these are both 0, then the PMOS ones are closed now, so these are connected to 5 volts and these are open. If we make this 0, 1, then this one's closed. We get a connection this way. The output's still 1. We have 1, 0. The 0 here will close this one. It goes up to there. And it's only when they're both 1 that these become open and these both become closed, so the output's 0. Well, remember, a NAND gate is low only when both inputs are high. So these 4 transistors put in this form actually a NAND gate. Well, how can we make an AND gate? Well, before we look at that, let's look at a NOR gate, which is we take the 2 PMOS ones and put them in series to 5 volts, put the 2 NMOS ones in parallel to ground. I claim this is going to give you a NOR gate. Let's see if it does. If they're both 0, then both of these PMOS ones are closed, and we're connected up to 5 volts, gives you a 1. However, if either one is a 1, this is a 1, it's going to close this one, goes to 0. If X is a 1, it'll close this NMOS one, goes to 0 or ground. And of course, if they're both 1, they go to ground. So this is a NOR gate, which is 1 only if both inputs are 0. Now remember, we need the PMOS ones to go up here to 5 volts. We need the NMOS ones to go to ground. So to make an AND gate, that's just a NAND NOT. So we really need 6 transistors here, because now all the PMOS ones are here, all the NMOS ones are here. So this was the NAND gate we just did, and then we just NOT it again, and that gives you an AND gate. So we see that NAND gates are actually easier to make than AND gates. And similarly, to make an OR gate, we need to take a NOR gate, these 4 transistors, add these 2, NOT, and we end up with an OR gate. Again, PMOS ones all going up to 5 volts, NMOS ones all going to ground. Okay, finally, let's talk a little about transistor-transistor logic. These were developed back in the mid-60s, the so-called 7400 series. They're now becoming obsolete with the development of programmable logic devices that we'll talk about in the next lesson. But transistor-transistor logics are still around. They're very cheap, and if you just need an inverter or an AND gate or an OR gate, sometimes they're still useful to use. although, as I say, they're becoming obsolete. They require 5 volts. The 5 volts goes here on pin 14. In this case, the ground would be connected to 7. So this 7404 has 6 hex inverters, or NOT gates, in them. 7408 has 4 AND gates in them. You can see how they're connected. Shows you the pin numbers. This would be 5 volts, this would be ground. 7432 has 4 OR gates, so with this small chip you can get 4 OR gates. The 7400 is a quad 2-input NAND gate, so these are 4 NAND gates. The 7402 is 4 NOR gates, and the 7486 is 4 exclusive OR gates. And there's all kinds of other ones. Here's a 7421, a dual 4-input AND gate, so you get 4 inputs in. You'd come in pins 1, 2, 4, and 5 and come out 6, for example, in that one. And the 7430 is actually an 8-input NAND gate. Well, there are lots and lots of different 7400 chips that you can choose from. As I say, they're becoming obsolete, and as we move to programmable logic devices, which we'll talk about in the next lesson.